Hello, welcome to Maths with EJD. In this video, I'll talk about the bisection method, and of course, this is the fourth video overall, but it's the first video when it comes to talking about the methods for root finding for nonlinear equations. So roots of nonlinear equations, and here we're using bisection method to find the roots. And the basic idea, as we are going to see here under the introduction, is this: that the bisection method, as the name implies, right, you are bisecting, you are dividing into two equal parts. So the bisection method is it's a bracketing method used to find roots of continuous functions. Okay. Um, it works, it works by narrowing down an interval where a root lies by narrowing down where a root lies by repeatedly um halving halving the interval. So you're bisecting the interval by repeatedly halving the interval and selecting the sub interval. You select the sub interval where the function changes sign, sign. Okay. Now, well, I think I should have done this before now, but I think I'll still do it. Talking about, generally, if you talk about methods for roots of nonlinear equations, this should have come first. I think I feel it's necessary to refer to this. So, I mean, bisection is the first one in it. So I'm going to still go back to that. So generally, if you look at the methods for roots of nonlinear equations, they are broadly classified into two. You have 1 point, should I think, let me put it this way. You have 2 point methods, 2 point methods, and you also have 1 point methods, 1 point methods. So if you look at them, for the 2 point methods, right? Uh, two, two, you need two values. How do I put this? Okay. Solution lies, yeah, I think this is the idea. Solution lies within an interval, That's why it's 2 point methods. Say an interval, say A comma B like this. You have a solution in between. That's why it's called the 2 point method. But for the 1 point method, an initial guess, um, solution begins with an initial guess. I think that's a better way. Solution begins with an initial guess, Okay. So that's one level to this. Then what if we talk about the specific methods? So methods, the methods basically here are bisection, which we've started talking about already. And here you talk about secant also. But when you come to this place, on the other hand, the methods for 2 point methods, okay, yeah, bisection and secant, 2 point method. Then the methods for 1 point method, you talk about uh, fixed point iteration, fixed point iteration method, and then you have Newton-Raphson. So these are the four things we are going to consider: Newton-Raphson. So like I said, it should have come before I started defining bisection. So now our focus is on bisection method, like I said already, and I already was told you that it's actually a bracketing method where you look for the roots within an interval, basically. So let's go for that now and face it squarely. Bisection method, which I have started defining already. So let's go for it. Now, um, like I said, the bisection method requires that you look for a solution within an interval. So let's go for it. So the next thing I want to talk about will be the steps. What steps do you need to take for bisection method? Steps for bisection method being being one of the methods under the 2-point method. Steps for bisection method. Okay. So the first step is to choose initial points. Choose initial points A and B such that f of A and f of B have opposite signs. Have opposite signs. That is, what that means is that if you multiply f of A and f of B, the value is negative. It's non-positive. It's less than 0. Okay. So the product of f of A and f of B is less than 0. That's the first step. So once you get those 2 points A and B, such that f of A multiplied by f of B is less than 0, the next thing is you compute, since you're bracketing, right, you're halving, compute the midpoint. Compute the midpoint C, which is equal to A plus B over 2. So you add the two together and divide by 2. Then the third step is to replace. So you now replace A or B with C, depending on where the sign changes. We're going to see this as I demonstrate with an example. Then the fourth step, you repeat. So you repeat until the desired tolerance is achieved. The desired tolerance is achieved. So at step 5, for step 5, right, the desired solution is reached if the absolute value the desired solution is reached if the absolute value of f of C is actually less than epsilon, where epsilon is the tolerance limit. I mean, less than or equal to, right? Where epsilon is the tolerance limit. Okay. The desired solution is reached if f of C is less than or equal to epsilon, where epsilon is the tolerance limit. So in this case, C will be whatever C gives you that condition will be the solution. Okay. Okay, so let's take an example to drive home this point. Okay, so find at least find at least one root find at least one root of the, or let me put it this way. Um, of course, find, okay, let me do this. Find the roots of f of x equals x cubed minus x minus 2 within the interval, within the interval 1 comma 2, given the tolerance limit, given the tolerance limit, epsilon equals 0.01. Okay, that's what we have right there. Now, normally you'll see that um because, okay, let's come to the solution, right? So what we want to solve is f of x equals x cubed minus x minus 2 equals 0, right? And we are given the interval, this is like our a comma b equals 1 comma 2, okay? And we have the tolerance to be 0.01. So these are the information we need. Now, the generally speaking, right, where you should stop is determined by the tolerance. But in some cases, you could also be told to do just a number of iterations. So whether you hit the tolerance target or not, it doesn't really matter, right? It doesn't really matter. But generally speaking, if you're writing, in fact, I have a computer Python code for this, which I'm going to show you by the time I'm done doing it manually. In fact, I'm not going to hit most likely because you're going to see the strengths and weaknesses of some of these methods as we go on. So for instance, bisection method is particularly slow. So to get to the get to the desired solution given the tolerance can take a lot of iterations. So because of that, we can use computation to finish it up. So that's what we have to solve now. So the first thing you want to do is you want to check if a solution actually lies, if a solution actually lies within 1 comma 2. We want to check if a solution actually lies there. And the way to do that is just to say, do f of 1. Okay. So this is A, right? This is B. So do f of A, which is equal to, of course, f of x is x cubed minus x minus 2. That is f of 1, which is 1 raised to power 3 minus 1 minus 2. That is 1 minus 1 minus 2. So that is minus 1, I think, or rather minus 2. Yeah, 1 minus 1 is 0, then you have minus 2 left. Okay, so take note of the sign. The sign is negative. Then you have f of b. So f of b is f of 2, which is 2 raised to power 3 minus 2 minus 2. So that is 8 minus 2 minus 2, which is 4. So you see, this is negative and this is positive. So because the signs are different, right, then it automatically means that a solution actually lies. So if the signs are the same, then no solution lies there. So you say since f of A times f of B is equal to it's less than, of course, f of A times f of B is like minus 2 times 4. That is minus 8. And this is less than 0. So since f of A is less than 0, then then a solution lies in the interval in the interval 1, comma 2. Okay, so you can now go on. In fact, normally you may not be given the interval, so you may be required to start looking for where the solution lies. So in that case, if you're not given 1, 2, for instance, you can just start from 0. So if you substitute 0, you discover that that's going to be negative. If you substitute 1, you discover that if you substitute 1, just like we've done, it's negative also. So if you put 0, it's negative. If you put 1, it's negative. So automatically, no solution lies between 0 and 1, because if you substitute those values, they give you negative values. So the signs are the same. So if you multiply, you're going to get something positive. So no solution lies there. But if you substitute 2, you discover that the solution is positive. I mean, what you get is positive when you put it into the function. So it means that a solution actually lies within 1, comma 2. So I mean, so it means you can, so once you see these two together like that, solution lies there. So you can now begin to look for the solution within that interval. Okay. So now we know there's a solution within 1 and 2. So we can start with the process. So this is how to go. I like to make this table to make things very easy. So you have your A, which is equal to 1, and you have your B, which is equal to 2. So you already know from what you did, when you substituted 1, the answer was negative. So put minus here. When you substituted 2, the answer was plus. So put plus here. So what you're looking for now is this C. So maybe I can call it C1, okay? Let's call it C1. Now, and to get C1, C1 is simply the same thing as A plus B over 2. That means you have 1 plus 2 divided by 3. So that means that C1 is equal to 1 plus 2 over 2, sorry. 1 plus 2 over 2. 1 plus 2 over 2. That is 3 over 2. So C1 is 1.5. So since C1 is 1.5, so that means that you can now check. So you have to, each time you get a result like this, then you check for f of C1 or whatever C you get. So f of C1 is equal to f of 1.5. So for f of 1.5, that means you have 1.5 raised to power 3, because don't forget the f of x you had. So that's x cubed minus x, 1.5 cubed minus 1.5 minus 2. Now this actually gives, this gives minus 0.125, minus 0.125. So this is what you have. So this is negative, right? So this is negative. So that means that C1 is given negative. So that, since the idea of bisection method is that there's no solution if the signs are the same. So here you have the sign to be the same. So this, you have to cut off that half. So it means that the solution basically lies between C1 and B. So so this is the first iteration now. So this is first iteration. First iteration. Okay. Now, for second iteration, we go again. So we now know the solution is between C1 and B. So we go again. This is okay. Now second iteration. Second iteration now. Okay, I mean, there's something I did not remember to do here. So you check for the tolerance. So the absolute value of f of x, f of C1, all right, is actually absolute value of minus 0.125, which is 0.125. So you see that this is still greater. This is greater than 0.01. So we have not reached where we are looking for. So iteration continues. Iteration continues. So this is, so each time you get a solution, you want to check. So 0.15 is still bigger. Absolute value of that is still bigger than the tolerance 0.01. So iteration continues. So the second iteration now is this. So now you have cut off A, because solution does not lie between A and C1. And you have C1 here, which is negative up here. And you have B, which is positive up here. So, but then the value of C1 is 1.5 and the value of B is 2. So now we need C2. So we need C2. So how do we get C2? C2 is simply C1 plus B all over 2. That is 1.5 plus 2 divided by 2. So that is 3.5 divided by 2. That is 1.75, I believe. Yep, that's 1.75. Yes, that's 1.75. And now that you have 1.75, what do? We come up here again and find f of C2. So f of C2 is 1.75 raised to power 3 minus 1.75 minus 2. And by the time you simplify that, you get 1.609375. So the absolute value of f of C2 is actually 1.609375. So you see, the other one looked hopeful, but now we are back to something very big. So that's why bisection method is really slow. So you can see this value now automatically is greater, in fact, far greater than what we even had before. So f of C2 is still greater than 0.01. What does that mean? It means that iteration continues. Iteration continues. So we can go for the third iteration. Okay, now, I mean, this is positive now. If you do it, this is positive. So this is positive now. So if the signs are the same, you cut it off. So you cut this portion off. It means the solution does not lie between C2 and B. So the solution clearly lies between C1 and C2. So we go again for the third iteration. So now we have third iteration. So for the third iteration, solution lies between C1 and C2. So you have C1, which is, what is C1? 1.5. And C2 is 1.75. 1.75. So, and it's minus plus, right? This is minus, this is plus. Okay. So now we need C3. We need C3. So for C3, we know C3 would just be C1 plus C2 divided by 2. That is 1.5 plus 1.75 divided by 2. So that means that C3 is, how do we compute that? Yes, I just want to go straight if possible. So this is 5 2. So that is 2.25, right? 2.25 over 2. So C3 is 1.1. I guess something is not right. 1.625. So 75. So 5, then 5 plus 7, 12. Then 1 plus 1, 2. Okay, this is 3. Yeah, this is 3. So that is 3.25. 3.25, 3.25 all over 2. So C3 now is 1.625. Yep. 2 in 3 is 1. 2 in 12 is 6. 2 in 5 is 2. Yeah. So C3 now is 1.625. And so what do we do next? We go for f of C3. So f of C3 is 1.625. So 1.625 raised to power 3 minus 1.625 minus 2. So if you do that, I mean, punch your calculator and you get 0.666015,625. So again, you see that the absolute value of f of C3 is actually, this is still greater than 0.01. So what does that mean? Iteration continues. So you can see this can be really slow. You're going to see faster methods as we progress. Again, the value here is positive. So this is positive. And what that simply tells us is that the solution does not lie between C3 and C2. So the solution now lies between C1 and C3. So that's the third iteration. So let me do one more iteration. Even if it doesn't meet it, then we can complete the rest with Python code, which I'm going to show you after now. So let's go for the next iteration. That's the fourth iteration, because we have not met our goal of, having something less than the tolerance value. So we go for the fourth iteration. Fourth iteration. So here we know that now the solution lies between C1 and C3. So C1 is 1.5, C3 is C3 is 1.625, 1.625. So C1, f of C1 gives a negative value, f of C3 gives a positive value. F of C3 gives a positive value. I mean, positive in that you don't hear it's positive like this. That's what that means. Just like F of C2 here is also positive. That's what we mean by positive, right? When you substitute the value, what you get. So here it's negative. So maybe I should even do that. This is positive here. Okay, the first one was negative. This is also positive. That's what we brought up here. So now the solution lies between C1 and C3. So now we need C4, okay? So, and we know C4 is going to be C1 plus C3 divided by 2. That is 1.5 plus 1.625 divided by 2. So that means that C4 is equal to, we have 2, 5. Yeah. Then 6 plus 5 is 11. We carry 1. That's 3.125 over 2. So C4 is 1.5625, right? Yeah, I believe so. 2 in 3 is 1. So 2 in 11 is 5. 2 in 12 is 6. 2 in 5 is 2. Then 2 in 10, 5. So that is C4 is 1.625. So now we got another, we have C4, which is another possible solution, just like we've been getting. So here we had C2 to be this. The first one we had C1 to be this, right? So now we have C4. So what do we do with that? We look for f of C4. F of C4, that is 1.5625 raised to power 3 minus 1.5625 minus 2, minus 2. So in this case, that gives us 0.25219,726,5625. And this is positive. Okay, so that means this is positive like this. And then you see that the absolute value of f of C4 is still greater than 0.01. So we have done 4th iteration. So that means that iteration continues until we have f of C something that is less than 0.01. So iteration continues. Iteration continues. So, but of course, I won't bother about the 5th iteration, but I'll just set it up and leave it there. So we go for the 5th iteration, which I'm not going to complete. I'm just going to set it up. 5th iteration. Now we see that the solution lies between C1 and C4 because it doesn't lie between C4 and C3 because they have both positive signs. So we have C1 and C4. So C1 is equal to 1.5. C4 is equal to 1.625. Right, is that correct? Nope. C4 is 1.5625. 1.5625. And what about the signs? The signs are minus plus. So you have minus plus. So normally we should go for C5, but let me complete the rest because it's taking too much time already. So let me just go to Python and take care of the rest. Okay. So with Python, we can take care of what is left. Interestingly, this Python code, I have put it in the description, so you can just copy and paste to your Jupyter notebook and run it. So you just check the description box under this video. You'll find the code right there. I'm talking about numerical analysis, and then bisection method is what we have dealt with so far. So coding makes things very easy. So you see, I've been iterating several times and it's just expanding and expanding. So with coding, you can just take care of that in a blow. So look at what like if I do the view and I put the line numbers. So line 1, we have a function, we define the function. So we define bisection method, which is going to take a function, and then you have a b, that's the interval, then the tolerance. Now, interestingly, since it's programming, the smaller the tolerance, the more iterations you have to do. So here I've even increased it to one times 0.00001. So that's even way smaller, but because we are coding, it's easy. So we can go as high as maximum 100 iterations on this one. So imagine we've done only four iterations, and it's already getting tiring, but with coding, it's very fast. So in line 2, we declare the condition that if f of a and f of b is greater than 0, then we say that the function does not change sign in the interval ab. That means no solution lies. If the signs are the same, then you return none. So you count, you do an iteration counter 0. Then while b minus a over 2 is greater than tolerance, you remember b minus a over 2 is greater than tolerance, then you have c to be a plus b. So b minus a over 2 is greater than tolerance. That's talking about the function we've defined, right? That's the tolerance condition. Then line 8 tells you where you define all the C1, C2 have been doing. So c is now a plus b divided by 2. Then line 9 is saying if f of c is 0, return c. That means you're evaluating the values in the function. So else if f of a times f of c is less than 0, that means b is equal to c. Else a is equal to c. Then iteration counter plus or minus. So you are incrementing the iterations. So if iteration counter is greater than maximum of the iteration, then you now print maximum iterations reached. So we have set it to go for 100 iterations. So if 100 iterations are exceeded and if it reaches 100 and we still don't get the answer, it just tells us maximum iteration reached, and it will just return us whatever value we have at that point. It just gives it to us. But if the tolerance is reached first, so there are two conditions now. If it reaches 100 iterations, it stops. Whatever it has at value, it gives it to us. Then if the tolerance condition is met, it will just stop because we have reached the actual condition. So here now, this is where we are defining the actual function in line 22. So define f of x, which returns x cubed minus x minus 2. Then in lines 25 and 26 and 27, that's where we are actually doing the actual work. So you apply bisection method. So root bisection is now whatever you have done with bisection method 1, 2. So you can now do this 1, 2. So which is our limit. So then you now say root found using bisection method just gives you root bisection, and you just go. So you see everything we've been getting has been so far. You remember C1 was 1.5, C2 was 1.75, C3 was 1.625, C4 was 1.5625, and so on and so forth. So as it keeps going like that, you see that the root found ends up going to 1.5213. So this is like where this around the solution that you get after 100 iterations. So this means that this is a more reliable solution of the problem. So you see, coding can just help take care of that in one blow. So just like I did the other time, you discover that there was no solution between 0 and 1. So what I'm going to do here is I'm going to change the interval to 0, 1, and to tell us that there's no solution in that interval. So it is going to output this line 3. The function does not change sign in the interval. So if you run that, see, so it tells you the function does not change sign in the interval. So root found using bisection is no root. So that means there's no root between 0 and 1. Just like if you put 0, it's negative. If you put 1, it's negative. So you can't get roots as far as the two signs are the same. So this has been a long video, but I think it's worth it. So if you have not subscribed to this channel, go ahead and do that, because after now I'll be talking about the second method. I'll go through the same process, and of course also talk about Python code for taking care of that. So hit the notification bell so you can always get alerted when a new video is released. Then comment, let me know how helpful these videos are. Don't forget to find the code in the description box. Let me know if there's a topic you'd like me to teach or a problem you'd like me to solve, and like and share so that more people can have access to this great learning. Till I come your way again, enjoy maths. Bye.